So let's restart. So good afternoon or good morning for those that are other parts of the world, maybe good night for some. So thank you so much for attending the seminar. And this seminar, I thank a lot Professor Henk Wymeersch for his for accepting the talk, giving the talk. Okay. I will start with a brief introduction to Professor Henk Wymeersch, who he obtained his PhD degree on electrical engineering applied science in 2005 from Ghent University in Belgium. He's currently a professor in communication system with Department of Electrical Engineering at Chalmers University of Technology in Sweden. And prior to that, prior Chalmers, he was a postdoctoral researcher from 2005 until 2009 with the Laboratory of Information and Decision Systems at MIT, Massachusetts University Institute of Technology. And he, of course, served as associate editor of a lot of IEEE transactions. So the most, maybe the last one or most recently was in communication letter, transaction on wireless communication, also a transaction on communications. And he is senior member of IEEE Signal Processing Magazine editorial. And I would say that from since 2024, he is a fellow of IEEE. So congratulations for this. This has been achieved this year. This fantastic news. His current research interests include, of course, conversions of communication and sensing in 5G and beyond 5G context. And the title of his talk of today is Radio Localization and Sensing, of course, the path from 5G to 6G. A quite very interesting, let's say, a topic where we see that the accuracy of localization and the weight of sensing is growing up from 5G to 6G. So very important parameters and very important topic. So Professor Henk, I give you the floor and thank you again. Thank you so much. Go ahead.
Thank you, Carlos, and thank you for the invitation. It's really my pleasure to speak to this esteemed audience, and it's nice to see some familiar names in the attendee list. So I'm located at Chalmers, which is in Gothenburg here on the west coast of Sweden. Many of you maybe have not heard of Gothenburg. It's Sweden's second largest city and home of Volvo. At Chalmers, I'm part of the communication systems group. We are 11 permanent researchers working on many areas of physical air communication, including vehicular communication, hardware limited systems, 5G, 6G, fiber optic, localization sensing, information theory, AI. So basically, I think no matter what area you can think of, we are active in physical air communication. My specialization is on radio localization sensing, and that's what I will talk about here today. So first, let me talk about a little bit about the vision for 6G. Let's see if this works. Yes. So this is a figure I took from 2 letters I published 2 years ago with my colleague Gonzalo Seco Granados, which provide a kind of brief overview of radio localization sensing. And this figure shows on the x-axis different location uncertainties, so target performances. On the y-axis, different deployment areas, and then the vertical lines represent different use cases. The different blobs represent different radio technologies. So you see here GNSS, which can meet almost all of the requirements for nearly all use cases, but needs a clean outdoor environment. You see 4G and 5G going all the way down to 1 meter, ultra wideband pushing down to 10 centimeters. And then there's this vision for 6G to meet these extremely demanding applications as cooperating robots, digital twins, and extended reality. And now the vision here goes down to approximately 1 centimeter. I should say, in all honesty, that about, let's say, 5 to 10 years ago, I had a similar slide where the blob that is now 6G used to be 5G. So the target a long time ago for 5G was around, let's say, between 1 and 10 centimeters uncertainty. But this was not realized. And then the blob moved a little bit to the right, and now the 6G blob is there. So it's not clear if we will be able to meet this extreme target of 1 centimeter. There's formidable challenges there, but at least it's a vision that drives the research community. Now, since I assume that I talk mainly to a communication audience, I want to spend a little bit of time talking about the foundations of localization sensing. So one thing that's important is to understand what are the performance metrics. So in communication, you care about spectral efficiency, coverage, rate, and so forth. In localization or positioning, you care about the quality of the estimated location. So for instance, you could measure this through the accuracy, which represents the error in location that can be attained in some statistical sense, like an RMSE sense. In order to get good accuracy, as we will see soon, you need high resolution. So resolution refers to the ability to resolve the multipath in different domains. Another important performance metric is the latency. So that's the time between an application asking for the position estimate and the position estimate being available to that application. And part of the latency is, of course, the over-the-air transmission, but this is actually minimal part. And there's other secondary metrics, including update rate and so forth. So overall, I would say that positioning, so the determination of the position of the connected device, is a song of accuracy and resolution. The figure on the right shows some examples of how those performance metrics trade off from a 6G paper we wrote last year in Vehicular Technology magazine, showing on the x-axis the accuracy requirements, on the y-axis the latencies. You have different diagonal lines which represent mobility, so a higher mobility with a high accuracy requirement needs to be supported with very, very low latency. You have also the different blobs that represent the different applications, and the colors represent their availability. There's also some vertical lines which represent the 5G capabilities. And the main message for this figure is that, first of all, those metrics are all in trade-off, right? So if you want high accuracy with high mobility, you need very low latency, but also to show that 5G cannot meet some of the very demanding applications. When we go from positioning to radar-like sensing, as I said, positioning is a song of accuracy and resolution. Radar-like sensing is much, much more. It's a much richer area of research and applications. There's, first of all, many different kinds of sensing. There's monostatic sensing, where in this case, a base station emits a waveform with bounces of objects in the environment, and from the backscattered signal, the base station can map the objects. There's bistatic sensing, where one base station sends a signal to another base station and the second base station maps the objects. There's synthetic aperture sensing, where there's a moving base station in this case, integrating information coherently over time as it's moving. And of course, you have multistatic sensing, where there's more transmitters or more receivers. And I deliberately draw two cars in all of these pictures because going from positioning to sensing, it's not just about accuracy and resolution, it's also about detection performance, the ability to detect a weak target in the presence of a strong target. You can think of a pedestrian nearby a vehicle. And it's also about data association. So data association here refers to relating measurements taken, for instance, by these base stations to previously detected targets. And this typically adds a lot of complexity to sensing problems. Let's now delve a little bit deeper into the of accuracy and localization. Again, these are just foundations. We'll talk much more about 5G and 6G in the slides to come. So the localization error is a vector, in this case in 3D, between the estimated location and the true location. And from that, you can figure out some accuracy metric, like the percentile of the norm of the error or the root mean square error. So this figure here shows, for instance, a car sending signals to and from a base station. The base station localizes the car, but there's some error. This is very straightforward. However, I think accuracy is a metric that's only reasonable when you have resolution. So let's talk a little bit about resolution. Let me activate all the entries here. So suppose that you have a base station here, which is trying to sense multiple cars. So this is a monostatic base station emitting a waveform. The waveform goes over the air, hits all these vehicles, and goes back to the base station. In order for the base station to realize that there's 5 vehicles here, it needs to have resolution. This resolution can come in many dimensions. So you can have delay resolution, which is achieved through the bandwidth. You can have angle resolution, which is achieved through the number of antennas, or Doppler resolution, which is achieved through the integration time. And you need resolution at least one domain to be able to determine that there's 5 vehicles. Now, all of these domains have a rather similar form. So observations across time, across subcarriers, or across antennas are all a superposition of paths with complex gains, and then some so-called spatial frequencies. And these spatial frequencies can then be related to the different physical dimensions, such as subcarriers, antennas, or time. In some cases, these dimensions are coupled. For instance, Doppler and angle of departure are typically coupled, or are not available directly, but rather in beam space. This is often occurring, for instance, in millimeter wave communication with analog arrays. So what I show here on the right is a picture where there's, for instance, one target of interest in the middle, but there could be other multipath components. And the yellow box here is a so-called resolution cell. So this is a cell that the size of which depends on the bandwidth, integration time, and the aperture of the array. If we have less bandwidth, the size of the resolution cell grows. And that means that, for instance, these blue paths, they will blur in with the red path. And that means the paths will not be resolvable, and then there's no meaning to talk about accuracy. But let's talk about this in a bit more tangible way. So suppose, again, we have our base station illuminating a collection of vehicles, here 5 vehicles with monostatic sensing. Then what the base station would observe across subcarriers would be Yn, a superposition of the 5 vehicles, each with a complex gain. And then we have the delay, which manifests itself as a linear increasing phase across subcarriers plus noise. And let's now see how the base station observes this signal when we vary the bandwidth after applying an FFT. So if the base station has a small bandwidth, for instance, 6 megahertz, what it would see is a single peak here and some side lobes. So if the base station would try to decide how many vehicles there are, it would say, okay, there's 1 vehicle. If we increase the bandwidth, these side lobes become more pronounced, and we could maybe say there are 3 vehicles. Only when we have enough bandwidth, in this case 120 megahertz, we would be able to decide, actually, okay, there are 5 vehicles, and once we're able to find that there are 5 vehicles, then we can talk about the accuracy of each vehicle. And I think this is one of my main messages. So a lot of people are doing research in positioning and sensing and talk about accuracy, but they ignore the resolution aspect. So resolution is needed before you can talk about accuracy. Okay, so with these metrics in mind, let's now talk just very briefly about some of the foundations in terms of the measurements that you can take for localization sensing, how it's done in 5G right now, and what are the potential easy extensions, and then look towards 6G, and what are all the enablers and some of the challenges. So first of all, let's think about the typical measurements that you can take for positioning. The first measurement you can think of is signal strength. So this equation here is a standard path loss equation that you can read in any communication textbook, which tells you that the received power is a function of the transmitted power and the distance. And the further you're away from the transmitter, the more path loss you will have, so the lower the received power will be. And then in principle, if you know the transmit power and the receive power, you could solve this equation for the distance. And if you have distances to several base stations, you could localize yourself. While this is a widely used model, I think it's a very misleading model. If you look at measurements, these are now very classical measurements from Rappaport in the 1990s, showing what happens when you plot on the x-axis the distance between transmitter and receiver, and on the y-axis the path loss. So the further you are away, the more path loss you have. We see these lines here, and these represent these path loss equations. And then all the markers, they represent measurements. So what we see is that there's no one-to-one mapping. This means for a specific amount of path loss, for instance, 60 dB, there are many, many distances that could match the 60 dB. This means it is very difficult to extract location information purely from signal strength. And this also means that in practice, signal strength is not used for positioning, except for one case, which is called fingerprinting. So in fingerprinting, the idea is that each location would have a unique fingerprint, which is a vector of signal strength with respect to many access points. And by learning this mapping from the fingerprint to the location, we can build a positioning system. But this is not at all based on the path loss equation. So signal strength is not a very useful measure of positioning information. The most common metric is time information. So if we think about 5G, 5G uses OFDM. We transmit pilots across subcarriers. At the receiver, we would observe phase variations across the subcarriers due to the delay. And then by applying FFTs, we can find distances. Okay, so this is what's shown here on the right. We have a transmitter and a receiver. The signal arrives at the receiver after some time. The receiver does an FFT, and then based on these peaks, it can figure out the distance. Now, there's one caveat here, which is that the observed time of arrival depends on the distance between transmitter and receiver over the speed of light, of course, plus the bias. This is because typically a transmitter and receiver are not perfectly synchronized, at least not enough for positioning purposes. So this means that from one measurement from one base station, a user cannot even figure out one distance. The same happens in GPS. So in GPS, your terrestrial unit is not synchronized to the satellite, so you need at least 4 satellites to localize yourself. You need 3 for X, Y, Z, and then the 4th satellite to figure out your bias. In this figure, you see 2 peaks. So this means that there was a line of sight path, the first path, and probably a ground reflection a little bit later. Whether or not you can resolve those 2 paths depends on the bandwidth. If you have a little bit of bandwidth, the paths will blur into each other, and it becomes very hard to accurately localize. If you have a lot of bandwidth, the paths can be resolved and localization becomes possible. In addition to delay measurements, very common is also angle measurements. On the left, I show how angle of arrival operates. So you have a remote source sending a signal to a multi-antenna base station in this case. The base station can observe the signal across the array, which gives rise to this complex vector R. And under line of sight propagation, this complex vector R would depend on the channel gain, the array steering vector, which takes as argument the angle of arrival theta and noise. And again, this angle of arrival theta appears as a linear phase rotation that depends on this angle. So you can again estimate the angle of arrival with an FFT, and if there's multipath, your ability to resolve multipath depends on the aperture of the array, so the size of the array with respect to the wavelength. You can also do angle of departure, and both of these are part of the 5G standard, in which case the base station emits a sequence of waveforms S of t to the remote user. The remote user has a single antenna again, so it can only observe a scalar argument, and this scalar observation depends on the transmitted signal multiplied by the steering vector and the channel gain plus noise. The receiver can then sample this waveform and collect them over time, so it will get a bunch of observations of this form. And it can then collect those observations and estimate the angle of departure from the base station to itself, using methods, for instance, such as orthogonal matching pursuit or any beam space method. How this is done in practice is that the base station would generate signals S of t that illuminate different directions. And the user just measures the signal strength, and the direction with the largest signal strength would then be the direction of arrival. Again, resolution, the ability for the user to resolve multipath depends on the size of the array with respect to the wavelength. Once you have those measurements, you can put them together into different ways. So for instance, on the figure on the right, if we have 3 base stations and we measure the signal strength and it's pure line of sight, so we don't have any multipath, then we could constrain the user to lie on the intersection of 3 circles. If we measure delay measurements subject to clock biases with 3 base stations, we could be localized on the intersection of 2 hyperbola. If we have angle of departure measurements, we could localize user on the intersection of lines, and we could do any combination of the above. All of those localization problems are all of the same form, right? So you have an unknown X, your position, maybe with some nuisance parameters like clock bias or your orientation, the mapping, going, for instance, from position to distance, and then there's all the measurements, the distances, the angles, and so forth, plus noise. And then given Y we want to solve for X, and this is a standard nonlinear least squares problem, or maximum likelihood, or maxima posteriori, which are typically non-convex. So a challenge often lies into how to solve these problems in a way that is not computationally too heavy. So this was all about positioning. If we now look at sensing, so this is how typically sensing works in a traditional non-5G like automotive radar context. We have here a car generating an FMCW waveform. So these are waveforms which are chirps. They have 0 instantaneous bandwidth, but span a large overall bandwidth. And they are constant in amplitude, so they're very amenable for low complexity hardware. The signal bounces off objects in the environment and returns. We filter, down, convert, and sample. And then we have an observation across frequency and time, the so-called fast time, slow time matrix. We take in 2D FFT as we did before, and then we could see targets in the so-called range Doppler plane. Okay, so on the x-axis we have range. This is range with respect to the transmitter, as well as velocity. This is radial velocity with respect to the transmitter. And then the different peaks, they represent objects. So in this case, there are 2 objects in front of the car. They're both at, let's say, about 75 meters, but one is coming towards the car and the other object is moving away from the car. So this is all I want to say about the foundations of localization and sensing. Let's now move towards what's the status in 5G. So the typical approach for 5G positioning is based on time difference of arrival, which I already hinted at. So in time difference of arrival, we can imagine a user device and several time synchronized base stations connected to a server. The user device emits a waveform, a broadcast waveform, which is captured by all of the base stations, and each base station measures the time of arrival. So the time of arrival at base station I is a distance between the ith base station and the user over the speed of light, plus the clock bias of the user plus noise. To get rid of the clock bias, we take one base station as the reference and compute the differential measurements. And these differential measurements, they have no more bias. And the differential measurements geometrically determine a difference of distances. And a difference of distances spans a hyperbola. So if we have three base stations, for instance, here shown on the right, then we can draw two hyperbola, and the user must be on the intersection of this hyperbola. The main limitation for this kind of positioning is the resolution, right? Because the quality of this time of arrival estimate depends on the ability to resolve the line of sight path from any other multipath component. A secondary limitation to the performance is, for instance, the placement of the base stations and, of course, the presence of the line of sight. So this is the main workhorse for 5G positioning. Since release 16 in 3GPP, there's been many enhancements to complement this, for instance, with angle of departure or angle of arrival measurements with respect to the base station and so forth. Now let's think a little bit about what are some of the things we could add on top of 5G with very little extra difficulties, but that could enhance it. And now we go more towards research that we've been doing in my team over the past few years. So the first enhancement will be something called radio slam. And here the principle is as follows. So if you think about positioning, as I said, for time of arrival positioning, you need at least 4 base stations. If you just want to communicate, 1 base station is enough. So this means that in principle, you need many more base stations for positioning than you need for communication. To get around this, what we want to do is we want to treat the multipath components in the environment as friends rather than foes. So consider, for instance, this figure on the right. So there's a base station sending a signal in downlink to the user, and in green is a line of sight path, and in red are multipath components from objects in the environment. In traditional positioning, we only care about the green paths, and we want to have enough resolution to get rid of the red paths. However, this requires us then to have at least 4 base stations. If we now try to use the multipath, because the multipath carries some geometric information, maybe we can get around with fewer base stations. So let's look at this multipath component here that hits this wall. This multipath component is characterized by 3 unknowns, namely this incidence point, right? We don't know where the radio wave hits the object. So there's 3 unknowns. On the other hand, the signal path has many observations. We have a time of arrival measurement, that's 1 dimension. We have angle of departure measurements at the base station. If the base station has a planar array, that would be 2 measurements, azimuth and elevation angle of departure. If the user device has an array, we could also have angle of arrival, azimuth and elevation. So we have 5 observations and only 3 unknowns. And you can show through different ways of analysis that having a single base station and a single bounce reflection or scattering is enough to solve the localization problem, meaning to localize the user, to synchronize user to the base station, to figure out the orientation of the user, and to map the environment. Okay, so multipath can really be our friend under some conditions. There's no more synchronization problem, and you can even do it when the line of sight between the base station is blocked, provided you have enough multipath components. So this is just a simple animation. Let's see if this will work. No, it doesn't work. Okay, there was an animation here about a car moving around the base station and mapping the environment over time. If you want to know more about this research, we have a YouTube video of a collaboration project we did together with Lund University, Qualcomm, Ericsson, and several other companies in a vehicular context, where we show that this can actually work. Of course, there's lots of challenges related to calibration regarding to the geometry of where the buildings are, if they can be exploited or not. But in principle, single base station positioning is possible, and mapping the environment at the same time is also possible. A second enhancement you could think of is the signal optimization. So when you think about how conventional positioning works, is that the base station would send beams in different directions. The user would measure the signal strength of each of the beams, and then the beam with the best signal strength would give you the angle of departure. But this is a very naive way of designing the beams. For instance, if you know already that the user is around a certain region, you could design the beams to not illuminate where you know the user is not. And it turns out, through convex optimization, you can formulate optimal beam designs. You can formulate optimal beam designs for angle of arrival, as well as for angle of departure. These are shown on the right. And these beams, they look a bit weird. They have lots of ripple, and this is because actually the ripple is what is most informative for estimating angles, because they tell you differences among different directions. In the European HEXA-X project, we've shown that this can be used in practice in collaboration with Qualcomm. And we showed, for instance, that even though the beams can be relatively broad, for instance, 10 degrees in beam width, by using this optimized precoders or combiners, you can get sub-degree accuracy. And for more information, I refer you to these documents here. A third enhancement, and now we're going slowly towards the 6G field, is integrated sensing and communication. So consider this case here on the right, where there's a user, the car here, sending signals in uplink to the base station. At the same time, the signal bounces off objects in the environment, in this case, these people, and the backscattered signal can then be used by the car to map the environment. Now, there's been a lot of work on the trade-off between sensing and communication in different dimensions. So one of the dimensions we're considering here is the frequency dimension. So if you think about communication between a transmitter and receiver, and you're using OFDM, what is the optimal allocation of power across frequency? And the solution is water filling. So the water filling solution is what gives you the optimal rate. On the other hand, if you want to do radar sensing, so there's some targets in front of you, and you have to allocate power across subcarriers for radar sensing, what is the optimal solution? The optimal solution turns out to be that you should put more power on the boundaries of the spectrum and less in the middle. And these two strategies are conflicting, right? So if you want to do something good for communication, it will be bad for sensing and vice versa. And that's what we've studied in this figure on the right bottom, coming from these papers, where on the x-axis, we have a communication metric, namely the capacity. On the y-axis, we have a sensing metric, in this case, the ranging performance. And this blue curve here shows the Pareto optimal frontier. So on the top right, this red circle represents the water filling solution. So that's the solution of the power allocation that gives you the best capacity, but the worst sensing performance. On the left, we have a solution which gives you the best sensing performance, but gives you horrible capacity. So already in the frequency domain, we see this tension between communication and sensing. A lot of research has been focused on exploring this tension in the spatial domain by designing precoders that illuminate targets or illuminate the communication receiver, but this tension is also there in the frequency domain. We also have some demonstration activities going on right now together with Volvo cars, but these are not been completed, so I cannot report on them right now. These were just some advancements that you could think of in the context of 5G. Let's now look towards 6G. So over the past few years, I've been involved either directly or indirectly into several European initiatives, including the HEXA-X project, RISE-6G, HEXA-X2, 6G DISEC, the Islands project. And since the 6th generation research has started, there's been much more focus on sensing and on localization. And I think this is motivated on the one hand by the use case requirements, but on the other hand also by the capabilities of the network, the capabilities of the 6G enablers. And in particular, based on my knowledge from those projects, I would say that there are 9 enablers, but there's also 3 important challenges. So the first enabler is the variety of carrier frequencies. So in 5G, we had our sub-6 gigahertz band, we had our FR2 band around 24, 28 gigahertz. These bands will be complemented with sub-terahertz, maybe around 140 gigahertz for short-range applications, as well as by the new FR3 band between 7 and 10 and 15 gigahertz for longer range applications. And combined, of course, these bands can provide you a lot of bandwidth, okay? So maybe over 1 gigahertz, which is great for positioning and for sensing. And at higher frequencies, also the channel is more geometric, right? Because at these higher frequencies, the shadowing becomes very severe. There's less reflection, more scattering. So overall, there's only a very few visible multipath clusters, which provide a lot of geometric information. When we go to higher frequencies, already at 10, 15 gigahertz, we'll need antennas probably on both sides of the link, both at the base station and the user side. Once we have antennas on the user side, this allows us to estimate the 3D orientation of the user. And that's why often people say, when we go to 6G, we will be able to do 6D. 6D localization referring to the 3D position and 3D orientation. The fourth enabler is introduction of side links, again, after many years, which will enable relative as well as cooperative positioning. Cell-free massive MIMO networks with phase coherence, which provides a huge aperture for near-field positioning. The integration of sensing, localization, and communication, both as a trade-off, as we saw before, but also as a synergy, in the sense that if I know where objects are or where users are, I can avoid blockages or point beams towards users. The use of AI for data-driven solutions, especially for those problems for which we don't have a good model or for which the traditional methods are too complex. The use of reconfigurable intelligent surfaces to shape the environment. This is very common for communication applications to overcome line of sight blockage, but I think will be even more interesting for positioning and for sensing. And finally, the introduction of the sky segment, for instance, through UAVs or low Earth orbiting satellites to complement terrestrial base stations and provide positioning coverage everywhere. With all of these opportunities come also important challenges. And these I realized through kind of hitting the wall in different scenarios. The first one is hardware impairments. So when you think about communication, you care about the channel between your DAC and ADC, right? Whatever's in between those is the channel, including the hardware, including the propagation channel. For localization, that's not true, because for localization, you care about the angles, delays, and Dopplers hidden inside of that channel. So you're much more sensitive to these hardware impairments, and you need much more fine calibration. This brings me to my second point, is that when you want this extreme performance, when you want centimeter level accuracy, you need to be extremely well calibrated. It's not enough to say I calibrate one device and all the other manufacturers will be almost identical. Even small variations in the antenna elements, the gains, will lead to severe degradations in the positioning. There's also calibration in terms of the position themselves. If you put up a wreath on the wall, you need to precisely know its position, orientation for that wreath to be useful for positioning. Based on our experiments, for instance, with Ericsson, we've seen that even a base station that would move in the wind would lead to degradations of positioning, or if the orientation or tilt of the antenna panel is not exactly known. And a final challenge, and this is really a 6G new challenge, is that we should balance the KPIs with the KVIs. So the KPIs are the accuracy, latency, and so forth, and the KVIs are the key value indicators. So this refers to the trustworthiness of the system, to the sustainability, both economical and societal, as well as the inclusiveness of the system. And to address those KVIs in a way that's compatible with the KPIs and also mutually compatible is an important challenge towards 6G. So in our team and with our collaborators, we work on all these topics, and I could give a 1-hour talk on each of these topics, but I will not do that now. I will just highlight 2 topics. The first one is the integration of sensing, localization, and communication. On this, I just have one slide because I have a point that I would like to make. So I've taken this figure and modified this from Ericsson, where they talk about the integration of sensing and communication from different perspectives. And of course, integration of sensing and communication has many names. There's ISAC, JCAS, DSRC, HSC, and so forth, but in my mind, they all mean the same thing. So when we think about this integration, how can this be? So the first level of integration would just be that we reuse the sites for communication and sensing. So this means that we have a base station somewhere and we put a camera or a radar below, and the radar would be informing the base station where users are or where objects are. And that's one way of integration. The second way of integration would be spectrum integration, meaning that the base station is sometimes communicating and sometimes the radar would be sensing over the same frequency bands. A third level of integration would be to reuse the infrastructure. That means the base station is sending sometimes communication signals and sometimes sensing signals. The fourth level of integration will be integration at the waveform level. That means there's a unified waveform, probably OFDM, which would be used sometimes for communication and sometimes for sensing over different orthogonal time frequency resources. And the last form of integration is a complete reuse, where we use the same waveform for communication, positioning, and sensing with the same time frequency resources. And what's interesting is when you talk to people from academia and from industry, they have a rather different perspective. So when you talk to industry, they see the potential mainly on the left. So the integration of sites, spectrum, and infrastructure. Well, when you talk to an academic audience, I would say they mainly focus on the right side, where you reuse the same time frequency resource for communication and sensing. So for that reason, I think maybe in the middle is where things will really happen, right? That we have now pilots for positioning, and later in the future, we'll have pilots for sensing. In any case, I think ISAC is much more than just what's shown on the right. It's this whole span, and this allows for lots of interesting research questions. For instance, in the future, should we have dedicated positioning anchors that are just listening to sensing signals? What is the optimal waveform for sensing? Should we go back to FMCW? Should we use DFT spread OFDM? Should we go to new waveforms like OTFS? Should we have dedicated sensing pilots complementing the positioning pilots? How often should they be sent? Where should they be placed? Will sensing and communication be in synergy or in trade-off? How can we work across all of those different bands in a harmonious way? Can information from FR1 inform something about FR2? And then when we talk about sensing, there's of course radar-like sensing, like monostatic, bistatic, and support sensing, but there's also non-radar-like sensing. For instance, sensing gestures or sensing something in the atmosphere. All of these are important applications, potentially for 6G. The last topic I want to touch upon is the variety of carrier frequencies. So in the early days of 6G, I would say maybe around 2019, 2020, when people were launching big 6G initiatives, there was a lot of hype about sub-terahertz. Why? Because there was an enormous bandwidth available, and this would be one way to support extreme data rates. And then from a positioning and sensing perspective, this was very interesting because at these large bandwidths, at these high frequencies and the large bandwidths, we have very good delay resolution, which allow us to do centimeter level positioning. However, now, 4 or 5 years later, I think the enthusiasm for sub-terahertz has faded, and we realize now that it's very challenging to build such systems. And even if we can build them, they probably will only be used for very low mobility applications or very short range applications. And this has then renewed interest in the lower bands. Okay, so there's of course the FR1 band from 5G, the FR2, again, not used very widely anywhere in the world, but in between is this new band, sometimes called the golden band, sometimes called FR3, where we will have limited bandwidth, right? But this will be the band that will be mainly used. So then an important question is, how can we get accuracy and how can we get resolution at these low bands? Okay. To try to answer this question, we started a collaboration with Bosch about 1 year ago, where we look at a kind of complex vehicular urban scenario with lots of multipath and see how much does the limited resolution harm us, right? So this is a result from one of our papers where we show on the x-axis basically a user that is moving across a lane in the city, and on the y-axis the positioning performance. And there's a bunch of curves and there's a bunch of parameters. Basically, it's a sub 6 gigahertz system with 20 megahertz of bandwidth. And what I want to highlight is this black dashed curve and the red curve. So the black dashed curve shows the positioning error bound if there was line of sight only propagation. So if there was only line of sight and no walls, no floor, no anything, we would get about 1 centimeter accuracy. And practical algorithms could achieve this. That's not a problem. When we now add the buildings and we add the floor and we add the lampposts and everything, then we will have multipath. And if this multipath cannot be resolved by the receiver, this leads to degradation. How much degradation? And here you see this is orders of magnitude penalties, right? So for sub 6 gigahertz positioning, multipath interference is the main limiting factor. Okay, and probably for sensing, it will be much worse because of the clutter. So then how can we improve the resolution at these low frequencies? And I focus here in particular on FR1, where the bandwidth is very limited. I would say there are three, sorry, it's my time. There are 3 answers to this. One is machine learning, the other one is super resolution, and the third one is phase coherence. And I will stop in a few minutes. I just will go through each of these very quickly. So the first way to get resolution at lower frequencies is machine learning. And the idea here is that the channel impulse response is unique for each location, even in a very dense multipath environment, and changes somewhat smoothly over time. So the mapping from the channel impulse response to the location can be learned with supervised learning. And in case the richer the channel is, the more resolution in principle you would have. Practical methods have shown about 1 meter accuracy using Wi-Fi technology, so at similar bands, and with relatively low complexity for inference. Of course, you need to do lots of data collection for training. So this is one way of addressing the resolution problem at lower frequencies. Of course, as somebody who likes math, it's not very interesting because you just throw a deep neural network at it and it will solve the problem. If you look at more mathematical approaches, we can look at super resolution. And what I show here on the top is the same figure from before, right? So this was the monostatic sensing with the base station with 5 targets. And when we looked at this figure, we would say, oh, there's only 1 target. But that's not the whole story. So this figure here is just an amplitude. There's also a phase associated with each of these elements. And it turns out that the combination of amplitude and phase response is unique to having 5 targets with certain distances. This means if I had fewer targets, fewer cars, or they were at different locations, this profile would look different when I look at both phase and amplitude. So there's only one unique solution. It's of course hard to find that solution, but in principle it is there. And that's the principle of subspace methods or super resolution methods. So they try to find this low dimensional subspace in this high dimensional space. And if you can do this, for instance, using Esprit or music or methods like that, you have in principle unlimited resolution, right? There's no limit to the resolution. You can be 1 millimeter apart. And if you have enough SNR, in principle, you can localize, or you can separate those objects. In some cases, they are low complexity, but of course, you need very high SNR for this to work. And it's still complex for higher dimensions. If you want to combine many dimensions, things still become complex. The figure on the right shows some examples that we've done of going from this match filtering based processing to super resolution, and we can observe orders of magnitude gains even for complex vehicular scenarios. The final approach is to use phase coherence. So if we have many base stations and they are time coherent, we can do time difference of arrival. If they are phase coherent, they act like one large base station. This is also the principle of cell-free MIMO, of carrier phase positioning, of distributed radar systems, and actual large MIMO. So you can have extremely high resolution through phase information or near-field processing, but you have other challenges, and in particular, the complexity challenge. So this is what the figure on the right shows. So this is a cost function, like a negative log likelihood function that I want to minimize when I have only time measurements. So if I have time measurements only from several base stations, there's a global optimum. The function is not globally convex. By doing some geometric pre-processing, I can find this global optimum relatively easily. If I now make all those base stations phase coherent and I want to exploit this phase coherence, my objective function looks like this. So it's a very nasty objective function. There's a global optimum exactly at the true location, but it's extremely hard to find. So finding low complexity methods to solve these problems, I think, is one of the important challenges for years to come. And I would call this the needle in the haystack problem. With this, I would like to end this presentation. So I want to highlight that SIG-G will be the first generation with localization and sensing built in from the start. How we'll reuse these services is not very clear. The regime of high frequencies is very interesting because of the large bandwidth and many antennas, but we should not forget the lower bands, which will probably be the ones launched in the first generations of 6G. How to get high resolution at those bands is to some extent an open question. And I think this vision of having 1 centimeter absolute accuracy is a pipe dream. I think it is not achievable except for some imaging applications, but again, it's a good goal to work towards. There's many enablers, and each of them has a really interesting angle when we look at localization and sensing, which means also there's many unexplored questions for many years to come. And I always say I've been working on positioning now for 20 years, and only in the last 4 to 5 years, it's really become a rapidly increasing field, and I'm very excited about the future for this field. Thank you for your time, and I'm sorry I went maybe a few minutes longer than expected.
Thank you so much, Professor Henk. Really interesting topic. I mean, it fits very well to some of the researches that we are pushing here at TII, and maybe others partners also in the university. Thank you so much. So we have some questions actually. So one of our colleagues asked, what is the impact of increasing the number of base stations nodes, saying from 3 to 30 as an exaggeration of number, on the TDOA localization accuracy? So the question was basically behind is, can increasing the number of base station nodes overcome some of the mentioned limitations?
Yeah, so of course, having more nodes will provide you more geometric diversity. So that's an important aspect of positioning, so-called geometric dilution of precision. If you have more base stations around you, that will be beneficial for positioning. If you put more base stations, then they're also more likely to be closer, which means there's an increased chance of line of sight propagation. And also the SNR will be higher. So all of these help you for positioning. The only downside is, if you think about downlink positioning, all of those base stations will need to share resources, which means that you have to have some kind of sophisticated positioning reference signal that remains orthogonal among those base stations. But overall, yeah, it would help you a lot.
Okay. Okay, nice. So regarding the reconfigurable intelligent surfaces, the RISs, this is also one of the quite hot topic that we are working on TII. And the question is the RIS set to dominate localization over conventional base station is still uncertain? How you see maybe the impact of the roadmap of RISs regarding the localization? Is it really, let's say, an element that could be quite very interesting to support the localization for future communication? I mean, beyond 5G, 6G?
I think that RISs hold great potential for localization. Whether they will be really used, I think depends. First of all, if the industry sees that there's a benefit for communication. I think always communication came first. So if people see that for communication is useful, then I think for positioning also it will be useful. I do think there's lots of questions with RIS. When you think about for communication, you can put a RIS somewhere and configure that it works for communication. For localization, you need much more information to calibrate its position. So it's much more challenging to use it for localization.
Okay, okay. So this is how you see it. First for communication, and when it has a plenty role in the ecosystem of communication, then it could be maybe support for localization, right?
Yeah, localization will not come first.
Okay, okay. So on my side, I have a question. Okay, working also 20 years on waveforms and so on, and you maybe survived also to the question about changing maybe or looking for suitable, let's say, waveform for 5G communication and beyond. We have seen years before that the accuracy and the localization doing off-the-M and ultra-wideband, because of the waveform, is not the same. To which extent really the waveform can play an additional, let's say, support for localization?
I think there's a lot of misconceptions about that. So,
okay.
And I'm scared I'm gonna hurt some people's feelings, but I think what matters is that you have a certain amount of bandwidth and a certain amount of time, right? Okay. And then you can fill that in how you want. But in the end, for positioning, it's just a pilot signal. So it could be a narrow band, no, not a narrow band, but like a single carrier, BPSK, that would be for me equally good as an OFDM or OTFS from the positioning perspective. What matters, I think, is the complexity of the receiver and the transmitter. Right. So how quickly can we get the ranges and Dopplers and angles out of this observation? And that's why I think OFDM shines, right? Because it really enables this very low complexity processing. But I don't think we need to look at new waveforms, not from a positioning and sensing perspective.
Okay.
And I have lots of opinions about OTFS now, but I think I should save this for like after dinner conversation or something.
Yeah. Okay, I don't know if the audience, they have other questions or those curiosities discussed during the talk of Professor Henk. Okay, I don't see any questions actually. Okay, so Professor Henk, thanks so much, really. I think many of the points that you highlight here, maybe you will get some, let's say, exchange with you, okay, mainly maybe on the RISs or localizations. Also, we're working on other topics on localization. TDOA is also one of the, let's say, techniques that we are exploring in different fields. And I'm pretty sure that many of colleagues maybe come back to you on some specific question after this. Thank you so much.
It'll be my pleasure. I'm very happy to collaborate with TII. Thank you.
Super. Thank you so much. It was really a
Thank you.
pleasure. Thank you.
Have a nice evening. Bye-bye.
You too. Thank you so much. Bye-bye.